Okay, welcome all of you. Thanks for coming. Today again is the big exponential day. It is a very, very important piece of calculus. It comes up, I would say it's probably the #1 used new function there is in all of applications. So you want to pay attention to this one, no matter what your major is or what you're getting into, because exponentials are the biggie. So it's kind of as important, probably more important than just y equals x squared, just to give you an idea. So let's do the quiz and let's take a look. Okay, so here's your quiz. And we have this x squared y minus y to the fourth plus x equals 11. And we want to find the equation of the tangent line at the point 3, 1. All right, so to find the equation of the tangent line, we need a point and a slope. And the point is given. So we just need a slope. And to find a slope, what do we need to do? You guys should all know by now, kind of the whole point of this class.
Derive.
Yeah, you need to take a derivative. And in particular, this particular equation is an implicitly defined equation or function. And when you have an implicitly defined function, we need to use implicit differentiation. You can try to solve for y, good luck, not going to happen. But what we can do is we can implicitly take the derivative. So I'm going to copy it in. So let's take the derivative. So what we have is x squared y. What rule do we have to use to take the derivative of x squared y?
Product rule.
Yep, product rule. So let's take the product rule. So the derivative of x squared is 2x times the second, which is y, plus the derivative of x squared, plus x squared times the derivative of y, which is the whole point, and that's just, I'll call it y prime. Okay, then we go minus, and then we have to take the derivative of y to the fourth. What rule do we have to use for that one? What rule? For y to the fourth?
Chain rule.
Yep, chain rule and power rule.
Yeah.
Sometimes you don't even think about power rule because you're just always using it. So it's chain rule and power rule. Derivative of a function to the fourth is 4 times the function to the third. So it's 4y cubed. And then times the derivative of the function, which is y prime.
All right, I got that right.
Okay, and then plus. I hope you can all do this. What's the derivative of x?
1.
1. And what's the derivative of 11? Easiest of all.
0.
0. Okay, any questions so far? All right, so now, what do we do with this? Because again, you can blindly take the derivative, which is great, but what's our point? What do we need to do next? And it's easy. Or I think so. So what's the next step after you take the derivative of every term?
Keep the y prime on the left side?
You could do that, but we don't need to. Remember, I told you there was an easier way. What should you do next step to make it so much easier than solving for y prime at this point? It's easy. Yeah, we plug in 3 for x and 1 for y. Means you don't do any algebra. And my feeling is plugging in is easier than algebra. So we plug in 3 for x, 2x becomes 6. And then y was 1. So 6 times 1 is 6. X squared becomes 9. And then we have 4y cubed. Y is 1, so that's just 4. Plus 1 equals 0. Let me save this guy. So now we find y prime, and that one I can pretty much do that one in my head. 6 and 1 is 7. 7 gets brought over as a negative 7. 9 minus 4 is 5. That gets divided, and you just get negative 7/5. So y prime equals negative 7/5. Any questions so far? Okay, now y prime is the derivative geometrically. What is it? Very
It's
important.
slope.
Yes, the slope of the tangent line. So we now have the slope and the point, and then it's beginning algebra to find the equation of a line given a slope and a point. So let's do that. We have 3, 1, and we have negative 7/5. So what we can say is that y minus 1 equals negative 7/5 times x minus 3. I'm gonna leave it like that. That's fine. Again, I don't grade you if you simplify algebra or not. Sometimes that's the best way of writing it, like I just did. Sometimes it's better to, add 1 to both sides. I don't care, but I did the calculus. Any questions on part A? Do I make it look easy?
Yes.
It's how it is, right? And then you do it, and it's not always so easy. But like I said, the key is to practice a lot before the exam, so that it's nothing's too bad. Okay, now we want to find the derivative, the second derivative at the point 3, 1. All right. So what line should I use? I'm going to name them. This is 1, 2, 3, 4, 5. Which of those am I going to use? Yeah, I'm going to use line 2 to go work for the second derivative, because you can't find the second derivative after you plugged in values. Okay, you find the second derivative immediately after finding the first derivative. And one nice thing is that to find the second derivative, we can take that first derivative. We don't have to solve for y prime, because we can implicitly differentiate. So let's do that. So we have 2xy. We need to use a product rule. Maybe I'll go like comma, because there's going to be too many differences. So we take the derivative of 2x, which is 2 times y, plus 2x times the derivative of y, which is 2xy prime. Any questions on the first term? Okay, now we use the product rule for the second one. Derivative of x squared is 2x, and then times y prime. And then plus, we have x squared. What's the derivative of y prime? Yeah, y double prime. It's the whole point. That's what we want. Okay, and then we have minus derivative of 4y cubed, and that's going to be 12y squared times the derivative of y, which is y prime, times y prime, so times y prime squared. Any questions so far? Okay, then we're going to multiply that, and we're going to go minus 4y cubed times the derivative of y prime, which is y double prime. And then the 1 goes away, because when you take a derivative of 1, you get 0. Derivative of 0 is also 0. And there's our second derivative right here. Any questions so far? Okay. Now I want to note something. We know that we're at 3, 1. And why have we already done some of the work for plugging in? What line do we need to be able to plug in besides just plugging in 3 and 1?
Value of y prime.
Yeah, we already have our y prime as -7/5. So -7/5 is going to go in for y prime. Okay. And 3 for x, 1 for y. So now I'm going to plug in again. So we have y is 1, so 2y is 2. And then x is 3. So that becomes 6. And then y prime, remember, was -7/5. So, and we have 2xy and another 2xy. So that's 4xy prime. So 4xy prime, let's write this out, it becomes 4 times 3, which is 12, times -7/5. Maybe I'll just write as 12 times -7/5. And that handles those guys. Then we have x squared is 9. Y double prime. We have y squared is 1. So that goes away. Y prime becomes -7/5, and it's going to write as 7/5 because we're squaring it. And that's safe. Y is 1. So the y cubed goes away. And then we're there. Any questions so far? Okay, so the last step is solve for y double prime. And let's do that. Oops, let's one more time. There we go. So to solve for y double prime, then I'm gonna get lazy. I'm gonna move this guy over. And then we're supposed to subtract these guys. Okay, and then, well, let me do it. No, got to copy and paste it into the parentheses. Then I got to divide by 5. Okay, for my requirements, do I require you to do the arithmetic on a
No.
quiz or a test? Do you need to waste your time and, pop that into a calculator or something, or are you good here? What do you think?
Thankfully, good.
Yeah, that's it. You're done. Okay, because I trust it. You know how to put things in a calculator. Okay, what I want you to do is do the calculus. Any questions at all on the quiz, finding the equation of the tangent line using the derivative with implicit differentiation, and finding the second derivative using implicit differentiation twice? Any questions? Okay, it's a messy problem, but it's not a trick problem. Hopefully you don't think it was a tricky problem. It's hard to have an implicit differentiation problem that isn't messy. They're all messy. So this one is what it is. Okay, so now what I want to do is answer any questions you might have. Any questions about anything? We're kind of in between exams, so
Larry,
probably about
I have a question. I mean, I know it's a sort of level of complaining, but I feel like none of the second derivatives of y prime were on the homework. I had no practice on this at all. I know it was in class, but like, why would you give us a question on a quiz where it was nothing in the homework at all?
because the second derivative is just the derivative of the derivative. You're supposed to know that. It wasn't
Well,
like some
Technically,
fancy.
yeah, but I mean,
That's all it is.
Okay. I mean, and that's your opinion. I felt like it was a little. If you didn't watch the video of class, then I would not have known what to do. I took the derivative of the derivative,
Mhm.
so that's why. But I get it. But I'm
Right.
just saying,
But I
like,
did do it. But I did do it in the video in class.
there's no practice though. That's what I'm
Right.
saying. Like, how could we have been good at this already if there was no like problems to practice with?
Right. This is going to make you maybe a little frustrated or not. This is the practice. So here's the thing, and this is something maybe you're not getting. This is not a test. Okay. This is just like homework. What it does though is it gives you a little more practice on how a test is going to look. Does that make some sense?
Yeah, no, I get that. I mean, it's a fraction of 7% of my whole grade. I understand that. It's just
Yeah, it's no
that's
more than
what
your
I'm-
homework, right? In terms of the amount of points on your grade, it's no more than the homework. This is like homework. That's all this is. Would I give you a problem on the test that you've never done anything like it on the
That-
exam? No. I
That's
wouldn't.
really my point, Larry. It's that, like, yeah, I felt like this was something that we didn't have something to practice with before.
Exactly, and that's why it's a quiz and not an exam.
Okay, so this is the practice, and we're graded on it. I get it.
Exactly, but you're graded on but you're graded on the homework also,
Yeah, no, I understand that.
right? And the grade is very little. I mean, it's very little. You know, what one problem on one quiz is like very little. So that's just a note, is that this is practice. The exam, which is a week from Friday, that's not practice. And I won't give you anything, you know, that you've never seen anything like. Okay, obviously I'm not going to give you an exact same equation to find a derivative of, but you're going to have to do an implicit differentiation. I could give you a second, because now you've practiced, I could give you a find the second derivative. I'd feel comfortable doing that for the exam. Quizzes are supposed to be low stakes, low stress. Does that make sense?
Yeah.
So I think it's more of a way of thinking. And the quiz is no different than the homework. Okay. In fact, the quizzes and the homework are worth the same amount, which is very little. Exams, on the other hand, are different. Exams, I would not feel right giving you a problem that you've never seen anything like. And hopefully the exam that you took, you know, the exam one, every problem looked like something you'd done something similar to, right? But quizzes are different. Okay. So whether you like it or not, that's my philosophy. Is that I don't treat quizzes like exams.
I get it.
Yeah. And the other big practice with quizzes is it helps you practice the typing everything out and showing work. Whereas with your homework, there's no grading, there's no points for showing work. Does that make sense?
Yeah.
That's the other big difference. Okay. Other questions?
Yeah, is there a section in the homeworks where we can practice more of this same I get it, this is the practice, but where we could work out similar problems and not just go
The
over
the book has some.
Oh, okay.
Yeah. So the book has them, and the book also has example problems.
Okay, cool.
Yeah. And in fact, what I usually do when I prepare for lecture is I go to the book. And then I try and hit the key points that the book has. Okay. So yeah, the book definitely has them, and you know, and the book's free. So, you know, you can do as many as you want. And the odd problems are in the back of the book. Or I don't know if back of the book makes any sense anymore, because now you just click the link. Any other questions? Do you have an exam in the near future? It all depends on what the word near means to you. It's a week from Friday. So it's another 11 days. Is that near future? I don't know. But it's definitely not this week. I haven't written it yet. It's a little too early. I'll probably write it this weekend. Yeah, so that's when the exam is. And again, the syllabus has all the dates. Okay, and I doubt the only reason why they would change is that there was some like internet disaster or something like that. You know, hopefully that doesn't happen. But everything is pretty set in stone. Okay, and I got some really terrible news. Okay, and promise me you don't shoot the messenger on this one. The schedule of classes for spring quarter was sent to faculty. Okay, and we have no say in it, and it's all online. Sorry. I was like crying. Maybe you like it, but I'd rather meet you guys. So it looks like our whole year is online. Bummer. Okay, and I wish we could wait a little while, hope for a vaccine, and then decide then. But yeah, I was so depressed. So sorry about that. Yeah, maybe they'll change their minds or something, but no, they're publishing the schedule, I think, soon. Yeah, so again, the main thing, don't get mad at me for this. It was not my choice. Absolutely not. I think we should wait until January to make the decision. That's my feeling. But it is what it is. I have no say in it. I just do what they tell me. So, bummer. All right, so let's talk about derivatives. All right, so I want to do an example of a nice function. And it's a function we haven't done yet, but these are important functions. Let's look at f of x equals, I think I'll just call it y actually, equals 2 to the x. Okay, have you all seen this function before? Y equals 2 to the x. Is this a new function for you?
No,
Right, you've seen it, but have you seen it in this class?
have not in this class.
No, and there's a reason, okay? And you've seen this function, and I want to let you know something, that your pre-calculus teachers were just, I don't know, playing with you when they gave you this, okay? Because this isn't, without calculus, this is not a well-defined function at all. Works great if x is, say, 3 or something, 2 times 2 times 2, right? But what if x is pi? It means nothing, right? You can't go 2 times 2 pi times, right? Okay, if x is a half, you can call it a square root. But if it's something like pi or 2 pi or something like that, you can't do this. But with calculus, you can, because we can define for a rational number, when you have p over q, then you learn in pre-calc that 2 to the p over q is the qth root of 2 to the p. I don't know if you remember that, but that's what you learn in pre-calc. All right. So if you know it for all rationals, then what you can do is you define it for the irrationals like pi as a limit. So you actually need calculus to even define y equals 2 to the x, even though your pre-calculus teachers pretended like it was okay. My guess, right? Did any of your pre-calculus teachers say we can't do this? Or they all just did it, put it on the board, just assume that you wouldn't even ask any questions about it, right? Sound right?
I made the assumption.
Yeah. So let me tell you, in calculus, we can actually do it, because we define it for all rational numbers, and then we can take a limit as those rational numbers go to an irrational number, because an irrational number can be written as an infinite decimal, and then you can use each decimal place as the limit that you're taking, and you're taking the limit as the number of decimals go to infinity. Okay, and pi, for example, is a limit of rational numbers, right? It's, you do 3, then you do 3.1, then you do 3.14, you do 3.141, and then the 3.1415, et cetera, and you can take a limit, and that gives you pi. And so given calculus, we can actually define this using limits. Okay, I'm not writing this all out because it's a little technical, but I wanted to say it so that now we actually understand that this is a function that is defined on all real numbers, okay, which is nice. Okay, so we've now done the limits. That was the first part of calculus. But now what's our big part of calculus we've been doing recently?
Driving.
Yeah, derivatives. Okay. Let you know, just deriving means something different than finding a derivative. So deriving actually is like proving. It's a math word stuff. Just let you know. So we call it finding the derivative or taking a derivative. So what I think I want to do is go to Desmos, just look at it to convince you that, yeah, maybe we can take the derivative. What do you think? Look at this curve. Here's y equals 2 to the x. Does it look like the derivative exists? Do you see any issues with it?
No.
No, it's
Yeah, you
continuous.
Totally find tangent lines there.
Yeah, I have no problem on any point that I'm looking at saying that there's going to be a good tangent line. Do you see that? So that's the first thing, is that you can look at this and say, yeah, I'm going to be able to get a tangent line. Okay, visually. There's no issues. It doesn't all of a sudden go up when it wasn't going up to the left. And now on the right, it's going up a whole lot more or a whole lot less. It's nice and smooth. Do you see that? Okay. I'm not going to prove all this. I can only prove so much in our class, but I do want you to get the feel for it. And by looking at the picture, it should be pretty clear that the derivative exists at all points.
Larry, doesn't that eventually reach a horizontal asymptote though?
Never.
No? Oh, okay.
No, because if it did, that means that it could, that would mean that it has a problem with the domain, right? So horizontal, a horizontal asymptote. Yes, a horizontal. What's wrong with the horizontal asymptote? Sorry, I was thinking vertical.
Well, wouldn't that mean that you can't find a derivative at one point because there is no limit at that point?
Okay,
Or
so so maybe you're thinking vertical also. Horizontal is not
Okay,
a
maybe.
problem. The derivative of horizontal line 0, no problem. Do you see?
Yeah.
Yeah, horizontal is
okay.
not a problem. Vertical is the problem, right?
Well, I thought that if there is a asymptote, then technically as you approach it, then there's technically never a limit, which I thought was kind of the definition of or the restriction of finding a derivative. If there's no limit, then you can't find the derivative.
Only for a vertical asymptote.
Okay, gotcha.
Horizontal asymptotes have 0 as a limit, right? For the derivative.
Oh, okay, right.
Yeah, horizontal asymptotes have no problems. Vertical asymptotes are awful for derivatives, right? And that has to do with lines. The slope of a horizontal line is 0, not a problem. Slope of a vertical line is bad. Does that make sense?
Yeah, okay.
Yeah. So this is a horizontal asymptote, and there's no problem. And even if that didn't have a limit, it's okay as long as you can get every point. Negative 100 is still not having a slope of 0. It's close, very, very, very close to 0. Maybe 1,000 zeros before you hit it after the decimal place, and then you don't have a 0. But you still won't actually. You'll never get 0 for the derivative. You'll just get things really close as you go far left. Okay, so this is definitely smooth. Okay, you're not all of a sudden going up when you weren't before. Okay, there's no jerkiness. Is that clear? Okay, so there's no problem with this. So that tells us we can find the derivative. So I'm going to find it. This might even be our last time doing this before the final, using the limit definition, because that's all we've got. It's not like we can use a product rule or chain rule or quotient rule. There's 2 to the x, and it can't be written as something we know times something or anything like that, or divided by or a composition of functions. It's just itself. It's 2 to the x. But we can use the definition. And I could take the limit as h approaches 0 of, and now you got to remember, it's going to be f of x plus h. So it's 2 to the x plus h minus 2 to the x all over h. I'm going to make this bigger because it's really little. And by the way, that was dy over dx. Any questions on that?
No.
Okay, so now let's see if you remember. There's a rule of exponents that says that if you take something to something plus something power, what can you do with that 2 to the x plus h? Rule of exponent.
Say that
Who
again?
remembers what you, yeah?
Can you say that again, please?
We have a 2 to the x plus h. There's a rule of exponents about when you have an addition as the exponent. We can do something to it. So I'm focusing right there. Remember the algebra? It's not calculus, it's algebra.
That'd be like 2 to the x plus 2 to the h, or times 2 to the h, I mean.
Times to the h, good. So that was a little algebra rule. So let's do that. So we can write that as 2 to the x times 2 to the h. Any questions so far? So now look at the top. I have a 2 to the x times 2 to the h minus 2 to the x. Algebra-wise, what can I do? Yeah, I can factor out a 2 to the x. And notice that 2 to the x doesn't have any h's in it. I could factor it all the way outside the limit. So I can take that 2 to the x. And bring it outside. Any questions on the algebra so far?
No.
All right, so now the question is, what's the limit as h goes to 0 of 2 to the h minus 1 over h? Okay, and that's not something we've dealt with before. Do you all agree? So I want to take a look at something. So we want to look at 2 to the h minus 1 over h. And the idea here is we want to see what is that limit? Any questions on that? Okay, what is that limit? And it might help to take a look. And for example, and actually before I do that, if x is 0, for example, this goes away and that's all we have. So at 0, we just get that. So the question is, what is that limit as h goes to 0 of 2 to the h minus 1 over h? Now, I picked on the number 2. Okay, and I want to let you know, the number 2 turns out to be not the best thing to use. But I just wanted to do it because it was simple and you guys can kind of get a good feel for it. Okay, in particular, I'm going to take that 2 all over the place and just make it a b. I just did the 2 because you're more familiar with it. Where b stands for, base. So nothing's changed. I'm just making it a little more general so we can think about it now. Okay, so we now have b to the h minus 1 over h. Any questions on that? And we want to see, what is this? Is that clear? Okay, well, we want to say, well, what do we get when we have b to the h minus 1 over h? What kind of b's could happen? And here's a graph of 2 to the x. And that means that we're looking at x equals 0, at x equals 0, because if you look again, at x equals 0, this guy, b to the x, is gone. And we just get this interesting limit. Do you see that? So the derivative at x equals 0 is going to be this limit. Now, what would it be nice? What's a nice number for this limit to be? right? If you had your choice, again, that limit is the derivative at 0. What's the easiest possible slope of a tangent line you can possibly have? 1. Okay, now I want to do the following. I'm going to take that 2 to the x. I'm going to make it a b. I'm going to add a slider. And negatives are bad, by the way. Let's start at 1. Let's end at 10. Whoops, 10. And let's go step 0.1. Okay, so right here, for example, look at that slope. Is that slope less than 1 or is that greater than 1? The slope of the tangent line at 1.
Less than 1.
It's less than 1. I don't think I need much to convince you on that, right? I mean, I could prove it, but I'm not going to. But you could see it. Do y'all believe it? On the other hand, how about now? Now let B be 10. Is that slope less than 1 or is that greater than 1? Yeah, now it's greater. Do you agree? Notice that when I move the slope, it continuously changes. Do you see that? The slope itself is a continuous function. Well, we have a continuous function that's less than 1 over here and greater than 1 over here. So do we know that it must be exactly 1 somewhere? And if so, why do we know that? So we have a continuous function. The slope is continuous such that it's less than 1 over here. And then we go up and it's greater than 1. Do we know it must be equal to 1 somewhere? Yeah, that's the intermediate value theorem. And the intermediate value theorem says that if you're below a number and then you become above the number with a continuous function, then you must hit the number. Okay, so then that tells us there's going to be a number. And it's around there. Does that feel like, if you look at the tangent line, looks like it's about 1? Do you see that? It's not perfect, but it's not that far from 1. Any questions on that? Okay, it turns out that yes, there is an answer to does a slope become 1? But that number is not a nice, easy to write down number. And the person who came up with the number, his last name was Euler. Have you heard of Euler before?
No.
Yeah, sometimes you'll hear of as Euler. It's a pronunciation thing, you know. He's from somewhere in Europe. But the important thing to know is what is the first letter of his name, of his last name? Now it's a spelling question, not a math question. First letter of Euler? Yeah, it's E. And what they did is they named this number after Euler. And this number is E, and they always use lowercase. That I don't know why, because, you know, last names usually have a first letter capital, but we use lowercase. So we're going to use E to represent that number so that that derivative is 1 at 0. Any questions on that? So define. Definition. E which, by the way, is 2.7182811828, and then it doesn't keep going, by the way, and in fact then it changes, but at least for a while it's easy. So 2.718. So E. See how many it gives me. 2.71828, but it should give me more. How about 100 decimals? Math is fun. That's got to be good. Okay, well, we didn't get 100, but it's 2.718281828, and then it's 45904, et cetera, et cetera. It's a little like pi, except that this one actually tricks you into thinking that it starts repeating, and it doesn't. So this is the number. And I will let you know that this is, a lot of people think that of the irrational numbers, this is definitely in the top 2 for the most important irrational numbers in the universe. Okay, at least that's what we all think. By the way, when I say top 2, what is it tied with?
Pi.
Pi. Okay. And to let you know why it's not just me that says so, you've heard of SETI? Right? What is SETI? What's their goal?
Search for extraterrestrial intelligence.
Exactly. So what we have to think about is we have to get rid of our own culture, because if there's aliens out there, they're not going to think like us. You know what I mean? They're not going to have Shakespeare and that kind of stuff. But if they're able to listen to our transmissions, that means they're able to do math. And we're sending out prime numbers, digits of pi, and digits of E. In binary, by the way, because we have 10 fingers. That's why we use base 10. So we're doing it in binary, okay, with a hydrogen frequency, because hydrogen is the most important atom. So E is, we've decided that important as everyone in the universe, okay? And I'm a believer that there actually are others in the universe that are out there in space. They're thinking about E also. So E's got to be important, okay? And if you can handle, getting, microwave reception, that means you probably know calculus. Any questions on how important E is? Okay, well, the wonderful thing about that, okay, and I promised you this is going to be like the prettiest derivative ever, is what happens, what is the derivative of e to the x? And the hint is it's beautiful. It's, what is it? And I just proved it.
Would that be 1?
Not 1. Read the line of the proof. 1 was the limit part. I still have other parts. Derivative of x is 1, and e to the x is not the same as 1. Do you see it? So derivative of the x needs to be e to the x times 1. And that's e to the x. So that's a pretty special derivative. Okay. The only other function that you knew ahead of time, which is its own derivative, is 0. Derivative 0, 0. But that one's kind of boring. That's an important thing. But e to the x is like, I came up with this weird number, 2.7182818284559, et cetera, et cetera. And it has such a beautiful derivative. Any questions on this? So, by the way, here's something that this is going to be a really easy question, even though it looks hard. What is the 18th derivative? Oops, I think I need to go fraction. Of e to the x. What's the 18th derivative of e to the x?
E to the x.
Yeah, it's e to the x. Because that means, well, we took the first derivative, you got e to the x. We'll take another derivative. Derivative of the x is e to the x. Take another one. Derivative of the x is e to the x. You do this all day long, you'll always get e to the x. So if you had a 100th derivative of e to the x, it's still e to the x. Isn't that a beautiful function? Any questions on that? Okay, so this isn't just kind of important. This is the most important function there is. Okay, when you get into your higher level science classes, e to the x is everywhere. So let me give you, again, today is not the applications day, but I just want to say applications. E to the x is when you're looking at any kind of population growth or bacterial growth, that kind of thing, is you use e to the x. E to the x is really important in finances. So if you're looking at inflation, e to the x. Or if you're looking at a company that is uninhibited and just keeps growing, that's e to the x. If you're looking at statistics, so I want to see just a minute. There we go. Yep, he's there. So Quinn had to go through the names and make sure. So sometimes it sucks being my former student because I'm going to pick on you. So let's look at 1 over the square root of 2 times pi times e to the negative x squared over 2. So that's a it's a composition of e to the x and x squared basically. And Quinn, what is that?
Wait, sorry.
What happened? Huh?
Could you repeat that, please?
1 over the square root of 2 pi e to the negative x squared over 2. What is that in statistics?
I'm going to be completely honest. I'm not too sure.
That's the normal curve.
Oh, yeah.
Yeah. Whatever I ask you, it's got to be the normal curve because there's nothing else important in statistics, right? Yeah, so this is the normal curve. The normal curve, by the way, is the most important curve there is in the universe. Okay, and not just because I teach statistics, but in chemistry, that's how you define shells, for example. There's a normal distribution. In physics, quantum physics is all about normal curves. Everything you do has got normal curves in it, and just trust me on that. But typically, because it's messy, you have to wait until you get into upper division or graduate level of your subject and to see it, but it will come up. Any questions on this? Okay, so the good news is we know how to take a derivative of it. Any questions on that?
Actually, Larry, yeah, I mean, I know it's probably not relevant to this class, but that exact equation represents a curve, a normal curve.
Yeah, except it's not a normal curve, it's the normal curve. Because a normal curve usually means that there's a mean and standard deviation that could be anything. This is what's called the standard normal curve. It means mean 0, standard deviation 1. So I decided I could have done the a normal curve. It's a little messier, and that would be even harder for Quinn to recognize. So this is the standard normal curve, and it's very important. Okay, it's the PDF function for the normal distribution, which is the normal curve. Okay, any questions on that? Anyway, I figure I should give you some examples where it's really used, and this is going to be used for the rest of this class. Next quarter, basically everything now uses this. Okay, and by the way, sine of x, is sine of x an exponential or cosine of x?
To the first power, yeah, I guess.
Oh no, it is. But I'm not gonna write it down because you're not responsible for it. But the cosine of x is e to the x minus e to the sorry, it's e to the ix minus e to the negative ix all over 2. So you can write cosine in terms of e to the x's. And sine has something similar. So you don't even need sine and cosine because sine and cosine's derivatives are not as nice. So a lot of times you just jump into exponentials, but you have to deal with imaginary numbers. So that's the problem with that one. But even sine and cosine are exponentials, are e to the x's. So weird stuff, isn't it? Things that you may not have seen before. All right, so now that we've seen the exponentials, I want to mention something, and this is important. Let's go back to the graph. But now we can go to the graph and not look at b to the x anymore. Now we can look at e to the x. Okay, I know it doesn't look that much different than the 2 to the x curve, but this is the better one. Okay, and by the way, 2 to the x, what field do you think 2 to the x comes in often? Anyone know?
Computer science.
Yeah, that's computer science, and that's because computers are binary. And if you want to know the total memory capacity, that's going to be 2 to the x, where x is a number of wires, for example, or storage areas. So 2 to the x comes up a lot in computer science. E to the x comes up everywhere. And there's one other number that comes up as a b. And you've seen it before, probably. Anyone know? I don't see y'all jumping in. 10 to the x. Okay, and the only reason why you often do 10 to the x is 10 to an integer is just pretty to write down. 10 to the third is 1, 0, 0, 0, right? So it counts the zeros as a number. So if you're dealing with pretty numbers, then 10 to the x is often the way they write it. Okay, but we're going to be looking in this class. E to the x is the biggie. So now I want to look at e to the x and look at this graph. There's a function. Is this a one-to-one function? Right? Is this a one-to-one function? Does it have an inverse? And this is from pre-calculus. Yeah. Hopefully you know that if you draw a horizontal line, you'll never find a horizontal line that crosses more than once. Okay, you could draw a horizontal line below the x-axis and it has 0 crossings, or above the x-axis and then it has 1 crossing, and that makes it an invertible function. If you switch the x and y's and try to solve, you're not going to be able to do it. So what do mathematicians do when they know something exists but they can't solve it? Right, so if we write x equals e to the y and try to solve for y using algebra, you're not going to be able to do it. So what do mathematicians do? If you don't know, I'll tell you. They just use a word. They just make something up. So they call it something, and then they make you think that they've actually come up with it instead of named it. So we're just going to name it. And the name that they've done, and you've seen it in pre-calc, is ln. Okay, and we know it exists, but because we can't actually solve, all we can do is give it a name. So we're going to write down, by definition, if f of x equals e to the x, then f inverse of x is equal, and I'm not sure if it allows me to do, if it's got one. Let's see. There it is. Yeah. Have you seen that symbol before? It's got 3 little horizontal lines instead of 2. Do you know what that means? So that means defined as. So it means we're not going to try and prove anything. We're just going to define it that way. So we're defining the inverse of e to the x as ln of x. Okay. Any questions on that? All right. So now you got to remember what class we're in. We have this new function. And what's the goal of pretty much everything in this class when you get a function?
Find the derivative.
Find the derivative. And this is another, I mean, e to the x is so beautiful. The derivative is beautiful also. I mean, the inverse is beautiful also. So our question is, let's find the derivative of ln of x. Well, we know how to do that. The way you find the derivative of ln of x is the derivative of the inverse function. Let's write this down. D over dx of ln of x, or let me do it in general first. F inverse of x is equal to, but we had a formula just last week. So that's going to be a fraction. It's going to be 1 over f prime of f inverse of x. Do you remember that formula? Hopefully you do, because it's an important one. Well, that's 1 over. All right. Well, if f of x is e to the x, what's f prime of x?
E to the x.
E to the x. But we're not plugging in x, we're plugging in f inverse of x. Okay, so that means we're going to take f, because f prime is f, and that's the most important thing. F prime of x is f of x. So that's the same thing as f of f inverse of x. Now, by definition, what is f of f inverse of x? This is the definition of the inverse. So what is f of f inverse of x?
Is it natural log x?
No. Forget ln of any function. I could give you, say, 3x plus 7 is f. And then I have f inverse, and I take f of f inverse of x. What do I always get? In any example I give you, you always get exactly the same thing. It's not ln of x. And there's the definition of inverse that you got in pre-calc. I don't see y'all jumping in. So f of f inverse of x is x. Okay, I like to think about f inverse is, if f is going 2 steps forward, then f inverse is going 2 steps back. So if I first go 2 steps back and then I do 2 steps forward, where am I? If I started with x, I'm back to x. Does that make sense? Because f inverse is undoing what we did. So if you undo it and redo it, you're just back to where you started. Okay, and that was the definition of the inverse. So now I can state it as a theorem about logs, about ln. And it's a beautiful one. It says the derivative of the natural log of x equals 1 over x. Isn't that pretty? And I am going to Make it big in red because it's important and you need to have this one down because you don't want to have to like prove it every time. Any questions on these two big theorems? Okay, the derivative of e to the x is e to the x. The derivative of ln of x is 1 over x. Okay, which means now we can do all the other, derivative rules and all that, do everything we want. I am going to tell you that all of the rules or properties that you learn in pre-calculus still apply. That doesn't change. All that changes is now we can take derivatives. Okay, that's our new thing. So you are responsible for knowing the rules with logs and the rules with exponentials, because that's just algebra. Any questions so far? Okay, now I'm going to give you one. This is a tough question. It's going to be a nightmare question if I asked you to do on the test and you didn't have any prep first. Let's suppose, oops, I don't want to function yet. F of x and we could just call it y equal the fraction x times the cosine of 1 minus x times the square root of x plus 3 divided by oops, I don't need that, x plus 1 squared times 2x plus 1 cubed times 3x plus 1 to the 4th power. And the question is, find y prime. All right, how long would this take you? If I asked you to do this, and all you could do is what you know right now. Yeah, all day is probably the right answer. Okay, my guess is it wouldn't take all day because you would just say, forget it. Sound about right? Because you have better things to do with your life. Okay, but there's a much better way of doing this. And here's a kind of a general rule, is that if you have something very messy with products and quotient rules, then do the following. This is called logarithmic differentiation. What we do is we take this function and we take an ln of both sides. So we can rewrite this as ln of y equals, and now I'm going to take an ln of the right-hand side. Now, do you remember your logarithm rules? It's been a while maybe, but it's important. Do you remember your logarithm rules to find out what the logarithm is of a product or a quotient and powers too? Okay, this is algebra, not calculus. And you remember the rules, what you have to do when you have products, quotients, and powers. So if you have a product like x times cosine of 1 minus x, and you take a logarithm, what happens to that, the multiplication? Do you remember? I don't see you guys remembering. All right, if you don't jump in. So remember the log of a times b is the log of a plus the log of b. Do you remember that? Does that ring a bell at all? Okay, this is not calculus. This is pre-calc and algebra. So multiplication becomes addition. And what about if you have x divided by x plus 1 squared? What does division become? Do you remember?
Is it log of A minus log of B?
Yeah, it becomes subtraction. So here's the thing. Addition and subtraction are a whole lot easier in calculus than multiplication and division. Do you agree? Okay, and it even gets better than that. What happens if you take ln of 3x plus 1 to the 4th power? Do you remember what happens to that 4?
You get to bring it to the front, it becomes a multiple.
It becomes a multiple. And multiplying by a number with derivatives is nothing. There's not even a chain rule you need there. So here's the thing. I can rewrite this as ln of x plus ln of the cosine of 1 minus x plus 1/2 times ln of x plus 3 minus, and maybe I'll do it this way, just for space reasons. So minus 2 ln of x plus 1, and then minus 3 ln of 2x plus 1, and then minus 4 ln of 3x plus 1. Any questions so far? All right. I know it still looks messy, but actually this isn't very bad because now it's addition and subtraction instead of multiplication and division, and there's no powers. So now, again, we want y prime. So now we go back and we do what we were just quizzed on today, right? What we worked on Friday, and that's implicit differentiation. So we need to find the derivative of ln of y. Well, we use the chain rule. The derivative of ln of y will be 1 over y times y prime, which is the same thing as saying y prime over y. Any questions on that? The left-hand side. What's the derivative of ln of x? So I'm over here.
1 over x.
That's 1 over x. And then plus. Okay. The derivative of ln of the cosine of 1 minus x, so we need a chain rule. So notice we're going to get a negative from the 1 minus x. We'll get a negative 1. Then we'll get another negative from the cosine. So that's 2 negatives, gives you a positive. And then we're going to have the derivative of the cosine is the sine of 1 minus x, this is chain rule, times the derivative of ln, and that's just going to be times 1 over x. Sorry, 1 over cosine of 1 minus x, since we're in chain rule. Okay, then plus. We're going to have 1/2. The derivative of ln of x plus 3.
Your screen's a little low. Thank you.
Yep, I just noticed that too. Thanks. The derivative of ln of x plus 3 is just going to be 1 over x plus 3 times 1 because it's chain rule. So it's going to be 1 over 2x plus 3. Whoops. Over here. And then we do the next one. Well, that's going to give you a minus, and we'll get 2 over x plus 1. Let's try one more time. Okay, and then do the next one. We're going to have a minus 3 over 2x plus 1 times 2 because of chain rule. And that's 6 over 2x plus 1. And the last one will be 12 over 3x plus 1. Still takes time, but nothing like it would if you had to use chain and product rule, which you just give up because it'd be so miserable. All right, there's one last step to get y prime by itself, which is what do we have to do to get y prime by itself?
Multiply everything by y.
Right. And what we can do is that gives us y prime by itself. Put this in parentheses. And I'll have it do on the next line because there's no space. Times y. Which is right there. So it's this top line times the bottom line. And that's the final answer. It's pretty messy. But we're able to do it in about 6 or 7 minutes. Any questions on that? This is called logarithmic differentiation. It allows you to do some really, really horrible derivatives in a bit messy way, but not anything like if you didn't have it. Okay, I want to, question? Okay, I want to mention a couple things. One is I've been picking on e to the x and ln of x, but we can do the following. Let's suppose we had 2 to the x. Well, 2 to the x is equal to e to the ln of 2 to the x. And just stick with me. I'll let you know that there's a reason that I'm doing this. It's like, why would I make it messier? But there's a reason. Ln of 2 to the x, there's a log rule when you have a power. What can I do with that x?
You can pull it to the front.
Yeah, I can write as x times ln of 2. And ln of 2 is a constant. So now what I can do is I can do the derivative of 2 to the x. What rule do I have to use to find the derivative of 2 to the x, given the fact that it's e to the x ln 2? In one word? What's the big rule for derivatives? Most important of all of them?
Power rule.
Power is the most useful, but I'm calling this important. And power rule we're not using on this one. There's a chain rule. Chain rule. There's like e to the u, where u is x ln 2. Well, what's the derivative of x ln 2? What's the derivative of x times ln 2? And the key is ln2 is a number. What's the derivative of a number times x?
That number.
That number. So it's just ln of 2 is the derivative of the inside. And the derivative of e to something is itself. So we just get times e to the x ln 2. But what is e to the x ln 2? That's 2 to the x. So we can rewrite this as 2 to the x times ln of 2. And there's your derivative of 2 to the x. Okay, and you could do this for any base, by the way. Nothing special about the number 2. Any questions about that? Okay, I could also do, because this is something you'll see outside of calculus. You'll never, in calculus, we always do e and ln. You'd never want to do another base. But in chemistry, for the logarithm, what's a big base for the logarithm that they use?
10.
10. Okay, and in fact, so we're going to take the log base 10, and a lot of times they don't even write 10, but I'm going to write the base 10. Because sometimes log will also mean ln. So I'm going to write base 10 just to emphasize it. ln of x. Well, you may or may not remember. My guess is you don't. There's something called a change of base formula. Anyone remember it? I'm going to open it up, but I don't expect anyone to, but just in case. Okay, it's ln of x over ln of 10. This is not calculus. This is just pre-calc. Is that you can always do that for any base. I could write log base 7 of x over log base 7 of 10, and that's still equal. And that's called the change of base formula. Do you believe me that you once saw that in pre-calc? Even if you don't remember it? Okay, so if we want to define the derivative of log base 10 of x, then that's the same thing as the derivative of ln x over ln 10. Do I need the quotient rule?
No.
No, I don't, because ln 10 is a number. And when there's a number in the denominator, there's no need to use the quotient rule. That's just going to be 1 over ln of 10. All right, that's just pulling the constant out. Times the derivative of ln of x. What's the derivative of ln of x? What's the derivative of ln of x? You want to memorize it, by the way.
1
E
over
to the.
It was 1 over x.
Oh yeah, that one.
Okay, and that's what you get. I'm going to write a little prettier because it's what most people write. Most people put them together. Oops. There we go. So it's 1 over x ln of 10. And was there anything special about the number 10? Had it been 4 instead of 10, would this work? And the answer is yeah. I didn't really use any facts about the number 10. So this will work for any base. You can, so in other words, you never need other bases because you can always convert it to ln. And ln is the best base in calculus by far, because look at the derivative. Derivative of ln of x is 1 over x, whereas if you have a different base, it gets messy. So It's 10:15. I'd like to stop here.